The de Havilland Comet emerged from post-war Britain as an object of absolute confidence. It was not merely an airplane. It was a declaration that the age of piston engines, propellers, and noisy cabins had ended. Its structure was smooth, pressurized, and clean in a way no commercial aircraft had ever been before. The fuselage was a thin-walled, stressed-skin cylinder designed to carry loads not through bulky internal trusses, but through the very aluminum skin itself. Every square inch of that skin was expected to work. Every rivet, every frame, every lap joint was calculated to distribute forces evenly, efficiently, elegantly. The engineers believed they had mastered the balance between weight and strength, between performance and safety. The Comet was designed to fly higher than weather, higher than turbulence, higher than its competitors. At those altitudes, passengers would sit in silence while the world curved beneath them. The structure was pressurized repeatedly, inflated like a metallic lung at each climb, then relaxed on descent. On paper, the margins were generous. In theory, the loads were well understood. In confidence, the aircraft was flawless. What the designers trusted most was the skin itself. Unlike earlier aircraft, where the fuselage acted largely as a container, the Comet's fuselage was a primary load-bearing component. It was thin because thin meant light. Light meant speed, range, and economic dominance. The aluminum alloy was state-of-the-art for the late 1940s, chosen for its strength-to-weight ratio and manufacturability. The windows, large and square, were a marketing triumph. They made the cabin feel open, modern, civilized. Structurally, they were framed carefully and reinforced. On blueprints, the stress flowed around them smoothly, redirected by doublers and stringers. In calculations, the structure held. In static tests, the fuselage survived pressures well above operational limits. To the engineers, the Comet was not reckless. It was bold, yes, but grounded in mathematics, metallurgy, and national pride. The flaw did not announce itself. It was not a single broken component, not a dramatic oversight like an undersized beam or a missing reinforcement. It lived at the intersection of geometry and physics, in a concept that was poorly understood at the time: stress concentration under cyclic loading. Every time the Comet climbed, the cabin was pressurized to simulate conditions thousands of feet lower than the surrounding atmosphere. This pressure differential forced the fuselage skin outward, placing it in tension. Every descent released that tension. This cycle repeated over and over again. Unlike a one-time overload, cyclic stress does not need to exceed the ultimate strength of a material to be deadly. It only needs to be persistent. At the corners of the Comet's square windows, the stress did not distribute evenly. Sharp corners interrupt the flow of force. They act as amplifiers. Microscopic regions at those corners experience stresses several times higher than the average fuselage skin. The engineers knew stress concentration existed, but its long-term consequences under pressurization cycles were not fully appreciated. Fatigue data for pressurized jet aircraft simply did not exist at the scale required. No commercial airliner had ever lived its life breathing in and out at 35,000 feet. The Comet was the experiment, and the experiment was flying passengers. The manufacturing process made the situation worse in subtle ways. The rivet holes around windows and lap joints were punched rather than drilled. Punching was faster, cheaper, and common practice, but it left microscopic cracks and cold-worked zones around each hole. These defects were invisible to the naked eye and insignificant in static strength tests. Under cyclic loading, however, they became nucleation points for fatigue cracks. With every pressurization cycle, those cracks advanced by fractions of a millimeter. No alarm sounded. No instruments registered the damage. The aircraft continued to fly, accumulating invisible debt inside its skin. Inside the metal, the process was relentless and silent. Aluminum alloys do not heal. Once a crack forms, the material ahead of it becomes stressed more intensely, accelerating growth. This is crack propagation, and it obeys physical laws that are indifferent to human confidence. Each cycle lengthened the crack slightly, turning a microscopic defect into a structural threat. The crack followed paths of least resistance, along rivet rows, around window frames, through areas where stress combined from multiple directions. To an engineer inspecting the aircraft on the ground, the fuselage looked pristine. Paint hid the scars. Panels were smooth. The airplane was doing exactly what it was designed to do, right up until the moment it no longer could. The failure, when it came, was instantaneous. At altitude, the cabin pressure pushed outward with thousands of kilograms of force. When the crack reached a critical length, the remaining intact metal could no longer carry the load. The fuselage skin tore open in milliseconds. The pressure differential did the rest. Air rushed out violently, ripping the structure apart from the inside. This was not an explosion in the chemical sense, but the physics were just as unforgiving. Structural members failed in rapid succession as loads redistributed faster than the airframe could respond. The aircraft disintegrated in flight, not because it was weak, but because it had been quietly wounded over time. The aftermath shocked the aviation world. Entire fleets were grounded. Confidence evaporated overnight. Investigators were faced with wreckage scattered over wide areas, pieces of fuselage twisted and torn in ways that defied conventional crash logic. Early theories ranged from sabotage to weather to pilot error. None fit the evidence. The pattern of damage suggested a failure from within, a betrayal by the structure itself. That realization was deeply unsettling. If the structure could not be trusted, nothing else mattered. The forensic investigation that followed was unprecedented in scope and rigor. Engineers reconstructed entire fuselage sections in laboratories. They submerged a complete Comet airframe in a water tank and pressurized it repeatedly, simulating years of flight in a controlled environment. Water, incompressible and safe, allowed cracks to reveal themselves without catastrophic rupture. Slowly, unmistakably, cracks appeared at window corners and rivet holes, exactly where theory had hinted but never proven. The aircraft failed again, this time under observation. The cause was no longer abstract. It was measurable, repeatable, undeniable. The conclusions rewrote the rules of aircraft design. Fatigue was no longer a secondary consideration. It became central. Windows became rounded, eliminating sharp corners and reducing stress concentration factors dramatically. Rivet holes were drilled, not punched, and inspected with new non-destructive techniques. Full-scale fatigue testing became mandatory, not optional. Pressurized fuselages were no longer trusted on calculations alone. They had to prove their endurance through simulated lifetimes of stress. The Havilland Comet paid the price of being first. Its failure was not the result of incompetence, but of incomplete knowledge combined with immense ambition. It taught the aviation industry that materials remember every load, every cycle, every breath an aircraft takes. From its losses came safer skies, stronger structures, and a deeper respect for the microscopic realities that govern macroscopic machines. The history of aviation is written with steel, ingenuity, and the will to challenge limits. Welcome to the Vault. Confidence does not fail loudly. It fails quietly, in assumptions left unchallenged and margins treated as absolutes. In the design offices at Hatfield, the Comet structure was treated as a solved problem. The mathematics of thin-walled pressure vessels were well known in theory, derived from naval engineering and industrial boilers. Engineers calculated hoop stress and longitudinal stress assuming smooth, continuous cylinders. Those equations worked perfectly if the cylinder remained uninterrupted. But an aircraft fuselage is not a perfect shell. It is perforated by doors, windows, antenna mounts, access panels, and hundreds of thousands of rivet holes. Each interruption distorts the local stress field, bending force lines inward and outward like water around rocks in a river. The Comet's designers acknowledged this distortion, but underestimated its cumulative effect. Their focus was static strength, how much pressure the fuselage could tolerate before rupturing in a single event. Static tests were impressive. Test sections were pressurized far beyond operational limits and survived. The data appeared to validate the design philosophy. What those tests did not replicate was time. They did not simulate thousands of pressurization cycles, nor the microscopic damage accumulation that occurs far below ultimate strength. Fatigue was still viewed as a concern primarily for wings and rotating components, not for fuselage skins assumed to operate well within elastic limits. The jet age changed that assumption fundamentally. At cruise altitude, the pressure differential across the Comet's fuselage skin was significantly higher than anything seen in piston airliners. Each cycle placed the aluminum alloy into tension, stretching it elastically. When the aircraft descended, the metal relaxed. On a molecular level, this repeated stretching caused dislocations within the crystal lattice to move, pile up, and concentrate around imperfections. Grain boundaries, inclusions, and surface flaws became focal points of damage. The material was not breaking, it was aging. The square windows were the most visually obvious stress concentrators, but they were not the only ones. The fuselage was assembled using lap joints, where one skin panel overlapped another. These joints created regions of uneven thickness and stiffness. Under pressure, the load did not distribute evenly across the joint. One layer carried more stress than the other, producing localized bending and secondary stresses. Rivets, intended to transfer load smoothly, instead introduced discrete load paths that further concentrated stress at each hole. Every rivet was a tiny experiment in fatigue. The choice to punch rivet holes compounded the issue. Punching shears metal by forcing a hardened tool through the sheet, plastically deforming the surrounding material. This leaves residual tensile stresses and microscopic tears at the hole edge. Drilling, by contrast, cuts material cleanly, producing a smoother hole with less residual damage. At the time, punching was industry standard and considered acceptable. The Comet revealed its long-term cost. Inside the metal, cracks initiated at these damaged edges. At first, they were microscopic, measured in microns. Under cyclic loading, the stress intensity at the crack tip exceeded the threshold for fatigue crack growth. Each pressurization cycle advanced the crack by an almost immeasurable amount. Engineers today describe this behavior using Paris law, relating crack growth rate to stress intensity range. In the early 1950s, this relationship was not yet formalized. The Comet flew in a gap between empirical knowledge and theoretical understanding. As cracks grew, they interacted with the surrounding stress field. When two cracks approached each other, their stress fields overlapped, accelerating growth. When a crack encountered a rivet hole, it could deflect, branch, or link up with another crack on the opposite side. The structure did not fail uniformly. It degraded asymmetrically, unpredictably, guided by the invisible geography of stress and defect distribution. Externally, nothing changed. The aircraft maintained performance. Pressurization systems functioned normally. Cabin crews reported no anomalies. Maintenance inspections, based on visual examination, found nothing alarming. Fatigue cracks of this scale cannot be seen without magnification or specialized techniques, which did not yet exist in routine airline service. The Comet continued to accumulate cycles, each flight quietly eroding its structural margin. When failure finally occurred, it did not begin as a large tear. It began as a crack reaching a critical length. At that point, the remaining intact ligament of metal ahead of the crack could no longer carry the applied stress. Fracture mechanics dictates that once the stress intensity exceeds the material's fracture toughness, rapid crack propagation occurs. The crack accelerated to near-sonic speed within the metal, ripping through the fuselage skin faster than any human could perceive. The sudden opening caused explosive decompression. Air rushed out of the cabin, carrying with it loose objects, structural debris, and enormous kinetic energy. The pressure wave propagated along the fuselage, overloading frames and stringers designed for gradual load transfer, not instantaneous shock. Structural elements failed in sequence, each failure redistributing load to the next weakest component. The aircraft did not simply lose pressure, it lost coherence. Investigators later noted that the pattern of wreckage suggested in-flight breakup rather than ground impact. Pieces of fuselage showed outward tearing, characteristic of internal overpressure. Windows and skin panels were found separated along rivet lines, indicating failure at joints rather than through the base material. These clues pointed away from sabotage or collision and toward structural failure, but the mechanism remained elusive until controlled testing could reproduce it. The grounding of the fleet was a watershed moment. Airlines, regulators, and manufacturers confronted a reality that had been theoretically acknowledged but never experienced at scale. Modern aircraft could fail not from overload, but from endurance. The investigation that followed transformed aviation engineering into a forensic science. Engineers treated the Comet not as a mystery to be guessed at, but as a system to be interrogated relentlessly. The full-scale water tank test became the definitive experiment. Submerging the fuselage allowed pressurization without catastrophic release of energy. As pressure cycles accumulated, engineers observed the birth and growth of cracks in real time. Dye penetrance and strain gauges revealed stress concentrations exactly where theory predicted they would be highest. The square windows, once symbols of modernity, became focal points of failure. Rivet rows lit up with strain, confirming that load paths were far more complex than assumed. The cause was no longer a matter of debate. It was fatigue driven by stress concentration in a pressurized fuselage, exacerbated by manufacturing practices and incomplete testing. Responsibility did not rest on a single decision, but on a culture that prioritized innovation speed over exhaustive validation. The Comet was not poorly engineered, it was undertested for the environment it created. From this failure emerged a new engineering discipline. Damage tolerance replaced safe life assumptions. Engineers accepted that cracks would exist and designed structures to tolerate them until detection. Inspection intervals were defined based on crack growth rates, not calendar time. Certification standards expanded to require full-scale fatigue testing, simulating multiple lifetimes of service before an aircraft ever carried passengers. The Comet's legacy is etched into every modern airliner. Rounded windows, fail-safe structures, redundant load paths, and rigorous fatigue analysis all trace their lineage to its losses. The aircraft that was meant to redefine confidence instead redefined humility. It taught engineers that materials obey physics, not optimism, and that the smallest flaw, given time and repetition, can dismantle the grandest machine. After the cause was identified, the investigation did not stop at explanation. It went deeper into quantification. Engineers needed to understand not just why the Comet failed, but how fast it failed, where it failed first, and how close the aircraft had been to disaster long before the accidents occurred. This was no longer about blame. It was about rewriting the physical limits of flight. The reconstructed fuselage sections revealed a disturbing truth. Significant fatigue damage existed long before catastrophic failure. In some aircraft, cracks had already grown to several centimeters in length while the airplane continued to operate normally. Structurally, the Comet had been flying on borrowed time. The margin between normal operation and total structural collapse was far thinner than anyone had imagined. The aircraft did not gradually weaken in a way that produced warning signs. It retained stiffness and strength until the final moments, then failed without negotiation. This behavior exposed a critical misunderstanding about materials under cyclic stress. Engineers had assumed that if stresses remained below the elastic limit, the structure would endure indefinitely. The Comet proved this assumption false. Fatigue does not require plastic deformation. It thrives in elastic regimes. Each cycle rearranges dislocations within the metal's crystal lattice, creating localized hardening and embrittlement. Over time, the material becomes less capable of redistributing stress. Instead of flowing smoothly, stress concentrates ever more sharply at cracked tips. The Comet's aluminum alloy, while strong and lightweight, exhibited relatively low fracture toughness compared to later materials. Fracture toughness defines a material's resistance to crack growth once a crack exists. In modern terms, the Comet's structure was vulnerable not because cracks formed. Cracks always form, but because once they reached a certain size, nothing stopped them. There were no crack arrest features, no tear straps, no alternative load paths. The structure was efficient, but efficiency came at the cost of resilience. The fuselage behaved as a single continuous shell. When part of that shell failed, the load had nowhere else to go. This is known as a lack of fail-safe design. In later aircraft, engineers deliberately introduce redundancy. If one structural element fails, others temporarily carry the load, slowing failure and allowing detection. The Comet had been designed for elegance, not damage tolerance. It was optimized for a world in which perfect manufacturing and perfect materials were assumed. The accidents forced regulators to confront an uncomfortable reality. Certification standards were built on incomplete physics. At the time, aircraft structures were certified primarily through static testing and conservative stress margins. Fatigue was treated as a secondary concern, addressed through operational limits and inspection schedules based on experience rather than science. The comet erased that comfort. Experience was no longer enough. The industry needed predictive models grounded in fracture mechanics. Out of this need emerged a new way of thinking about structural life. Engineers began to model crack initiation and growth explicitly. They accepted that defects were inevitable and focused instead on controlling their consequences. Inspection intervals were calculated based on how long it would take a crack to grow from undetectable to critical. Materials were selected not just for strength, but for fracture toughness and fatigue resistance. Geometry became a primary safety variable. Sharp corners disappeared from pressure vessels, replaced by smooth radii that reduced stress concentration factors dramatically. The comet's failure also reshaped testing philosophy. Full-scale fatigue testing became mandatory for pressurized aircraft. Entire fuselages were subjected to repeated pressure cycles in laboratories, simulating multiple service lifetimes. These tests were slow, expensive, and destructive, but they revealed weaknesses before passengers ever boarded. The industry accepted that the cost of testing was insignificant compared to the cost of ignorance. Manufacturing practices changed as well. Rivet holes were drilled and cold expanded to introduce beneficial compressive residual stresses, which slow crack growth. Surface finishes were improved to reduce initiation sites. Non-destructive inspection techniques evolved rapidly, driven by necessity. Ultrasonic testing, radiography, and later eddy current inspection allowed engineers to see beneath the surface, where fatigue truly lives. The psychological impact on engineering culture was profound. The comet shattered the illusion that advanced technology naturally equates to safety. It demonstrated that innovation without deep understanding carries its own form of risk. Engineers learned to distrust intuition when dealing with complex systems operating near physical limits. Data, testing, and humility replaced confidence and assumption. For Britain, the loss was particularly painful. The comet had been a symbol of national recovery and technological leadership. Its grounding ceded dominance of the jet airliner market to competitors who learned from its mistakes. Yet, paradoxically, its influence extended far beyond commercial success. Every pressurized aircraft that followed carried the comet's lessons in its skin. Every rounded window, every fatigue test, every inspection protocol was a quiet acknowledgement of what had been paid for in metal and lives. The final reports did not describe the comet as a failure of imagination, but as a failure of foresight. The engineers had imagined speed, comfort, and progress. They had not imagined how unforgiving repetition could be. Fatigue is a patient adversary. It does not announce itself. It waits, accumulating damage invisibly until physics reaches its inevitable conclusion. In the end, the comet did not just change aircraft design. It changed how engineers think about time. Structures are no longer judged solely by how strong they are on day one, but by how they age under stress. The airplane became not a static object, but a living system, shaped continuously by every flight it makes. This realization marked a turning point. Aviation entered an era where safety was no longer assumed to follow from strength alone. It had to be engineered explicitly, tested relentlessly, and verified continuously. The comet's skin failed, but in doing so, it exposed the microscopic truths that now protect millions of passengers every day. The story does not end in tragedy alone. It ends in transformation. From the silent propagation of cracks inside a pioneering aircraft emerged an entire science devoted to preventing them. The comet's legacy is not written in its wreckage, but in the invisible margins that now separate fatigue damage from catastrophe across the global fleet. In aerospace engineering, progress is rarely linear. It advances through confrontation with failure. The Havilland Comet confronted the industry with the reality that materials have memory, geometry has consequences, and confidence must always answer to physics. The transformation forced by the comet did not unfold quietly or gradually. It arrived as a systemic shock to the entire aviation ecosystem, exposing weaknesses not just in one aircraft, but in the intellectual framework that governed how aircraft were conceived, tested, and certified. Airlines demanded certainty that no engineer could honestly promise. Governments demanded accountability from a profession accustomed to deference. Engineers found themselves facing an uncomfortable truth. The tools they trusted had limits, and those limits had been crossed without being recognized. Before the comet, structural safety was largely deterministic. An airframe was considered safe if calculated stresses remained below allowable values with conservative margins. Failure was assumed to occur only when loads exceeded strength. The comet destroyed this assumption. It demonstrated that structures could fail catastrophically while operating entirely within their calculated stress envelopes. The failure mechanism was not overload, but endurance. Time itself became a load case. This realization forced a fundamental shift in how structural integrity was defined. Engineers were compelled to abandon the notion that an aircraft could be designed to remain crack-free throughout its service life. The idea was revealed as physically unrealistic. All manufactured materials contain imperfections. Microscopic inclusions, residual stresses, surface scratches, and geometric discontinuities are unavoidable. Under repeated loading, these imperfections evolve. The comet proved that ignoring this evolution was not conservative, it was dangerous. From this recognition emerged the discipline of damage tolerance. Instead of assuming perfection, engineers assumed damage. The new question became whether a structure could survive with cracks long enough for them to be detected and repaired. Structural design shifted from preventing crack initiation to controlling crack propagation. Components were no longer evaluated solely on ultimate strength, but on fracture toughness, crack growth rates, and inspectability. One of the most visible manifestations of this shift was the introduction of crack arrest features. Tear straps were added to fuselage skins, bands of thicker material designed to interrupt crack growth. If a crack initiated and began to run circumferentially under pressurization, the tear strap would blunt the crack tip, reducing stress intensity and stopping further propagation. This concept fundamentally altered fuselage behavior. A local failure no longer implied global collapse. Redundancy became embedded in the structure itself. Load paths were duplicated deliberately. Frames, stringers, and skin panels were arranged so that the failure of one element would redistribute loads gradually rather than instantaneously. This added weight and complexity, but the industry accepted these penalties as non-negotiable. The comet had demonstrated that structural efficiency without redundancy was a liability masquerading as elegance. Certification philosophy changed just as radically. Static tests and analytical margins were no longer sufficient to demonstrate airworthiness. Regulators required full-scale fatigue testing that replicated real operational conditions. Entire airframes were subjected to tens of thousands of pressurization cycles in laboratory environments, often exceeding their intended service life. These tests were slow, expensive, and destructive by design. Failure during testing was not only expected, it was required. Only through failure could weaknesses be exposed under controlled conditions. These full-scale tests revealed behaviors that theory alone could not predict. Secondary stresses emerged from interactions between components. Load redistribution followed complex paths that defied simplified models. Crack growth did not always follow intuitive trajectories. Engineers learned that aircraft structures were not collections of independent parts, but tightly coupled systems whose behavior could only be fully understood through holistic testing. Materials science advanced rapidly in response. Aluminum alloys were reformulated to improve fracture toughness without sacrificing strength. Grain size, orientation, and impurity control became critical variables rather than manufacturing afterthoughts. Heat treatment processes were refined to balance hardness and ductility, slowing crack growth once initiation occurred. Later generations of materials were evaluated not just for how strong they were, but for how gracefully they failed. Manufacturing practices were scrutinized with new rigor. Rivet holes were no longer punched indiscriminately. Drilling and cold expansion techniques were adopted to introduce beneficial compressive residual stresses around fastener holes, significantly slowing fatigue, crack initiation, and growth. Surface finish standards were tightened. Minor scratches that would once have been dismissed as cosmetic were now recognized as potential fatigue initiators. Inspection evolved from a routine checklist into a predictive science. Visual inspection alone was acknowledged as inadequate for detecting subsurface fatigue damage. Non-destructive testing technologies advanced rapidly under regulatory and operational pressure. Eddy current inspection allowed detection of small cracks around fasteners. Ultrasonic testing revealed internal flaws invisible from the surface. Radiographic methods exposed hidden damage in complex joints. Maintenance schedules were rewritten based on crack growth analysis rather than arbitrary intervals. The comet also forced a cultural transformation within engineering itself. Confidence based on intuition and precedent gave way to humility grounded in data. Engineers learned to distrust designs that appeared elegant but lacked exhaustive validation. The profession internalized the idea that systems operating near physical limits must be treated with suspicion, not admiration. Complexity demanded skepticism. Risk communication changed as well. The accidents demonstrated that catastrophic outcomes could arise from mechanisms that were slow, invisible, and statistically rare until they converged. Safety analysis began to incorporate probability distributions and worst-case scenarios. Engineers learned to account for low-probability, high-consequence failures rather than dismiss them as implausible. What mattered was not how unlikely a failure seemed, but whether its consequences were survivable. At its core, the comet exposed a subtle but profound form of engineering hubris. It was not negligence, nor arrogance in the conventional sense. It was the belief that existing knowledge was sufficient to justify unprecedented operating conditions. The engineers extrapolated beyond experience with confidence that physics would remain obedient. The aircraft reinforced this belief by performing flawlessly until it did not. The economic and geopolitical consequences were severe. Britain lost its early dominance in the jet airliner market. Competitors, observing the failure from a distance, incorporated the lessons without paying the same cost. Yet this asymmetry is precisely what gives the comet its historical weight. It absorbed the unknowns for the entire industry. Others advanced because it failed. In the broader arc of aviation history, the comet represents a pivot point. Before it, safety was assumed to follow from strength and conservatism. After it, safety became an explicit design objective requiring verification over time. Aircraft were no longer judged solely by how they performed on their first flight, but by how they aged under relentless repetition. Every modern pressurized aircraft carries the comet's legacy in its structure. Rounded windows exist not for aesthetics, but for stress distribution. Certification standards are written in cycles, not just loads. Maintenance programs assume damage rather than deny it. Safety margins are defined by fracture mechanics, not optimism. The comet did not fail because engineers lacked intelligence or dedication. It failed because they stood at the boundary of human understanding and stepped beyond it without realizing the ground had changed. In doing so, they revealed a truth that now underpins all of aerospace engineering. Materials remember every load, geometry magnifies every assumption, and time is the most unforgiving force of all. Aviation today is extraordinarily safe not because failure has been eliminated, but because it has been studied without illusion. That discipline was forged in the aftermath of the comet. Its skin tore, its structure failed, and an entire industry learned to listen to the quiet warnings hidden inside metal, before physics makes them impossible to ignore. The final lesson of the comet is not found in aluminum alloys or fracture equations. It is found in the boundary between ambition and restraint. By the time the investigation concluded, the technical questions had answers. Stress concentration, metal fatigue, crack propagation, and inadequate fatigue testing were no longer abstract concepts. They were quantified, documented, and embedded into regulation. What remained was a deeper reckoning. The recognition that engineering progress is not linear, and that the most dangerous failures are born not from ignorance, but from partial understanding combined with confidence. The comet was designed at a moment when aviation stood on the edge of a new era. Jet propulsion promised speed, altitude, and efficiency beyond anything previously imagined. Engineers had mastered piston aircraft through decades of iterative learning. They believed those lessons could be extrapolated upward, scaled into the jet age with only incremental adjustment. The comet proved that assumption wrong. Jets did not merely fly faster. They lived in a different structural environment. Higher altitudes demanded pressurization. Pressurization introduced cyclic tensile stress across the entire fuselage. The airplane was no longer just carrying loads, it was breathing repeatedly, under conditions no transport aircraft had endured before. This shift transformed the fuselage from a passive container into a dynamic pressure vessel. Every flight cycle became a structural event. Every ascent and descent consumed a fraction of the aircraft's finite fatigue life. The Comet was the first to experience this reality at scale, and it did so without the benefit of hindsight. The engineers believed their margins were sufficient. The aircraft flew smoothly, efficiently, and without warning, until it did not. That silence was the most dangerous aspect of all. The industry learned that catastrophic failure does not always announce itself with vibration, noise, or degraded performance. Sometimes it arrives fully formed, the final consequence of a process that has been unfolding invisibly for years. Fatigue is not dramatic. It is patient. It advances in microns, indifferent to schedules, reputations, or intent. The Comet taught engineers that the absence of evidence is not evidence of absence, especially when dealing with materials operating under repeated stress. Out of this realization emerged a new ethical dimension of engineering. Designers were no longer responsible only for making structures strong enough to fly. They were responsible for understanding how those structures would age, degrade, and ultimately fail. Safety became a life cycle problem, extending from design through manufacturing, operation, inspection, and retirement. An aircraft was no longer considered safe simply because it met specifications on day 1. It had to remain safe on day 10,000. This shift permanently altered the relationship between engineers and uncertainty. Before the Comet, uncertainty was managed through conservative assumptions and safety factors. After the Comet, uncertainty itself became an object of study. Engineers learned to ask not just whether a structure was strong enough, but how wrong their assumptions could be, and what would happen if they were. This mindset change may be the Comet's most enduring legacy. The cultural impact within aerospace engineering was profound. Confidence gave way to skepticism. Elegance gave way to robustness. Designs that appeared overly efficient were scrutinized rather than celebrated. Redundancy, once seen as an elegant excess, became synonymous with responsibility. Engineers learned that simplicity in appearance does not guarantee simplicity in behavior, especially in systems governed by nonlinear physics. The Comet also reshaped public trust in aviation. The idea that a modern airliner could disintegrate without warning was deeply unsettling. Restoring confidence required more than technical fixes. It required transparency, regulation, and a visible commitment to learning from failure. The industry responded by institutionalizing investigation, standardizing reporting, and treating accidents not as anomalies to be hidden, but as data to be understood. Aviation safety culture, as it exists today, was forged in this crucible. From a historical perspective, the Comet occupies a paradoxical position. It was both a technological triumph and a commercial failure. It proved that jet airliners were viable and desirable, even as it demonstrated that they could not be built safely using inherited assumptions. Other manufacturers, watching closely, incorporated its lessons and advanced rapidly. They succeeded not because they were smarter, but because they were second. Yet without the Comet, that success would have been delayed and far more costly. Someone had to confront the unknowns first. Someone had to discover, through loss, where theory ended and reality began. The Comet bore that burden. It paid the price of exploration in the harshest currency engineering knows. Today, when a modern airliner climbs to cruising altitude, its fuselage expands slightly, just as the Comet's did. Inside the metal, stresses rise and fall with each cycle, just as they always have. The difference is not that fatigue no longer exists. The difference is that it is expected, modeled, monitored, and managed. Cracks are assumed to be present. Structures are designed to tolerate them. Inspections are timed to intercept them. Failure is no longer treated as a surprise, but as a preventable outcome. Every rounded window on a modern aircraft is a quiet memorial to the Comet. Every tier strap hidden beneath paint, every fatigue test conducted before certification, every inspection interval calculated from crack growth data traces its lineage back to those early jetliners. The Comet's influence is not visible to passengers, but it surrounds them completely. In engineering, progress is often narrated as a sequence of breakthroughs. In reality, it is a sequence of corrections. The de Havilland Comet was both. It broke the sound barrier for commercial travel in spirit, if not in speed. It also broke the illusion that innovation alone guarantees safety. It revealed that mastery of physics is never complete, only provisional. The comet story is ultimately a story about humility. It reminds engineers that materials do not care about intent, reputation, or ambition. They respond only to stress, geometry, and time. A microscopic flaw, properly aligned with physics, can dismantle a machine that embodies the pinnacle of human ingenuity. That truth is uncomfortable, but it is also empowering. Once understood, it can be designed against. The legacy of the comet is not its failure, but what followed it. A global aviation system built on verification instead of assumption. An engineering culture that treats uncertainty as a design parameter. An industry that understands that safety is not a destination, but a continuous process of questioning, testing, and learning. The history of aviation is written not just in triumphs, but in the willingness to confront uncomfortable truths. It is written in steel shaped by equations, in aluminum scarred by fatigue, and in the discipline to listen when physics whispers before it screams. This is not the story of a flawed airplane. It is the story of how a single microscopic crack forced an entire industry to grow up. The history of aviation is written with steel, ingenuity, and the will to challenge limits. Welcome to the Vault.